Greetings, AP Chemistry students. Today we're going to be starting the second part of Unit 8, Acids and Bases, and we're going to be talking about buffers, which are a really important part of chemistry, as you will soon see. So here we go. So, first of all, thing to remember is that when an acid and a base react, that reaction goes essentially to completion, where H pluses and hydroxides combining to make water. The value of K is 10 to the 14th, because this is the reverse of the ionization of water, the Kw. And when you reverse a reaction, you take the inverse of the K. Don't forget that. They're going to ask you about it on the AP exam, probably. When a strong acid and base react, the pH of the resulting solution can be determined from the concentration of the excess reagent. So, for instance, if you know how many moles of hydroxide would be left over or H pluses, well, you just find the molarity of it, take the negative log of the molarity, you've got the pH or the pOH. A buffer, I'm going to show you how you make a buffer, and then I'll show you what a buffer does. So a buffer can be made in one of four different ways. The first is you take a weak acid and its conjugate base and you mix them together. So if you took, for instance, hydrofluoric acid and something that contains the fluoride ion like potassium fluoride, or if you take acetic acid and sodium acetate, that would make a buffer. You can also take a weak base and its conjugate acid. You can mix ammonia and ammonium nitrate, and that would make a buffer. A third way is you can take a weak acid and mix with it a limited amount of strong base. And I'll explain how that works real quick. So, if you have the weak acid, hydrofluoric acid, and to that you add some strong base, which is essentially adding hydroxides, then it would react to make water plus fluoride. So this reaction would go 100% to completion. And as long as you have an excess of HF, you set up an ice chart. If you had, for instance, 1 molar HF and zero 0.5 of OH, water doesn't matter. This reaction goes to completion. The acid-base reactions essentially go to completion if they can. So this will go down by 0.5, down by 0.5, and up by 0.5. So you would have weak acid and its conjugate base present. So that's how you make a buffer that way. And in a similar fashion, if you make a weak base with a limited amount of strong acid, that would convert some of that weak base into its conjugate acid. That also makes a buffer. But essentially, when you're done, you have a conjugate acid base pair in solution in your buffer. And what buffers do is they resist change in pH. So if you add an acid to a buffer, then that acid will react with the weak base that's present, converting that acid that you added into the conjugate acid of the weak base. If you add a base, it will react with the weak acid that's present and turn it into conjugate base. So essentially, a buffer converts any strong acid that you would add into a weak acid, or it converts a strong base into a weak base. It doesn't completely eliminate it, but it reduces its effect on the pH of the solution. So let's take a look at that real quick. If you have a buffer made of acetic acid or vinegar and sodium acetate, if you add a strong base, you're adding hydroxides. The hydroxides would react with the acetic acid to form water and acetate, which is your conjugate base. It's a weak base. If you add H pluses, you're adding a strong acid. The H pluses would react with your conjugate base to turn it into acetic acid. So like if you dump some hydrochloric acid in there, essentially it reacts with the acetate to turn it into acetic acid, which is weak acid, thus minimizing its impact on your solution. Now, there is an equation called the Henderson-Hasselbalch equation, which would allow you to calculate the pH of a buffer solution. So if you have a mixture of a conjugate acid-base pair, the pH of the solution equals the pKa of the acid plus the log of the concentration of conjugate base over the concentration of weak acid, or your acid. This is base over acid. This equation is on your reference tables. pKa is the negative log of the Ka. There's also the formula that would involve like POH and PKB, but we don't need to worry about that. Um, but a few things about this. If your acid and base conjugate pairs have these same molarities, then this fraction is equal to 1. The log of 1 is 0. And so, if you have equal amounts of weak acid and conjugate base, your pH equals the pKa. And your pOH would equal the pKb of the base that you're dealing with. Keep in mind, the larger the values of pKa, the weaker the acid. The larger the pKb, the weaker the base. Okay. So, we will talk more about pH and buffers later when we start analyzing titration curves. But if the pH of a buffer is less than your pKa, you have more weak acid present than base. And if it's greater than the pKa, there's more weak base present than there is acid. Because, for instance, if you have more base than acid, then this fraction is a number greater than 1. The log of that is a positive number, so your pH goes higher. If you have more weak acid than conjugate base, then this fraction is less than 1. The log of a number that's less than 1 is a negative number, and so your pH would go down as you have more acid present. You think about it, it makes sense. If you have more acid present, the pH goes down. If you have more base present, it goes up. So the last thing we're going to look at here is buffer capacity, which is related to how much weak acid and base you have present in solution. And what's called maximum buffering capacity is when you have an equal amount of your acid and base. So equal amounts of the conjugate acid base pair. And at that point, your pH equals the pKa. And if you were to look at the Henderson Hasselbalch equation, we'll talk a little bit more about this tomorrow. But only when you change the ratio of weak acid to weak base by a factor of 10 does the pH change by 1 unit. So, in other words, you can use up essentially like 90% of the capacity of the buffer before the pH changes by a value of 1 pH unit.